In section 5.2, we're going to continue from section 5.1 talking about natural log functions, but in this section we're going to talk about integration rather than differentiation, which we covered in 5.1. Okay, so there was one type of problem we couldn't do back in chapter 4 regarding the power rule, and that was the problem where we were trying to integrate x to the negative 1 power with respect to x. That problem we couldn't use the power rule on, because if we did, we would get x to the 0 over 0 plus c, and that doesn't make sense. We can't divide by 0. So that whole thing just didn't work for us. Well, as it turns out, when we integrate 1 over x, which is x to the negative 1 power, that we've defined as equal to the natural log of the absolute value of x plus c. Now, that should hopefully be maybe obvious in a way, because we discovered that the derivative of a natural log was 1 over x in 5.1. So of course, if we go the other way, the integral of 1 over x is equal to the natural log absolute value of x plus c. The reason that absolute value has to be there, and I'm going to kind of say this in every example we do, you're going to have to remember to put that absolute value around the x, because a natural log has to always be positive. You can never take a natural log of a 0 or a negative number. One little thing that the title of this slide might lead you to believe, and that is you might believe we're trying to take the integral of ln x with respect to x. That's not really what the title of this slide is talking about. If you want to figure out what the integral of ln x dx is, that answer would come in a Calc 2 class. So for now, all we need to know is that the integral of 1 over x dx is ln x. If you ever see an integral of an ln x, then that's going to be something along the lines of a chapter, or not a chapter, but a Calculus 2 problem. Okay, so let's put this new integral to use. Here we're integrating a set of 1, 2, 3, 4 things that is being added or subtracted, so we can take each of these integrals separately. Since we've moved on from chapter 4 and we've had a lot of practice taking integrals, I don't think any of you really need to write these integrals all separate, but I just want to emphasize that we're taking each of these integrals individually because we're using the sum difference rule. So when we integrate 6x squared, we'll just use the power rule, so we'll add 1 to the power, divide by that new power. When we integrate 4x, we'll add 1 to the power, divide by that new power, and now we can do the integral of 1 over x dx. The integral of 1 over x dx would be ln, and the key here will be the absolute value of x. The integral of 1 with respect to x is x, and then of course don't forget the plus c, and we should probably clean up those coefficients. So 6 over 3 is 2, so 2x cubed, 4 over 2 is 2, so negative 2x squared, minus ln absolute value x plus c. Okay, here we have the integral of 2 over x dx. Well, this one we can approach quite simply by pulling out that 2 in the top of the fraction. If we factor out that 2 to the outside of the integral from the top of the fraction, we'll just be left with a 1. And like you saw in this problem, or in this slide, the integral of 1 over x dx is just ln absolute value of x plus c, and of course that constant of 2 just stays in the front. That answer is perfectly acceptable to circle, nothing wrong with that. But this is an AP test question where I'm leaving out the answer choices. And this answer was not one of the choices. There's something we could do with this to simplify it, and hopefully you're kind of seeing this based on your experience with 5.1. But keep in mind, anytime you have a coefficient in front of an ln, we can move it to the inside of that ln as a power. And if we do that, we don't need the absolute value anymore. When you square anything, it'll always be positive. So that absolute value is actually not necessary anymore. So that's the answer I'm going to circle. But again, just realize the one before was acceptable. Okay, in this last example, I'm going to illustrate a very common mistake many Calc students will fall for. and that is this. The integral of 1 over x is dx. The integral of 1 over x dx is ln absolute value of x. That's not the mistake. The mistake is thinking that 1 over a function is equal to ln of that function. So be careful. That is absolutely not true. And to illustrate that, let's do this problem. So the funny thing is, you should kind of realize that that shouldn't be true because it's not a plain x in the bottom of this fraction. You'll notice this formula, 1 over x, that's just a plain x in the bottom of that fraction, 1 over x. In this case, we have 4x minus 1, which isn't a plain x, so we're going to have to do a u substitution instead. So we're going to call the bottom u. And you'll notice we have a dilemma like you heard way back in 4.5 when we were trying to learn integration by substitution. The dilemma is we're integrating a u with respect to x. We can't do that, so we need to go over to our u box and do a derivative so we can make another substitution. The derivative of u is du, the derivative of 4x minus 1 is 4 dx, and since there is no 4 in our integral in our problem over here, we're going to divide that 4 to the other side, so we have 1/4 du equals dx. This dx gets swapped out with this dx and becomes 1/4 du, and just like you saw back in chapter 4, we'll move that 1/4 to the front of the integral. And now we can take this integral. The integral of 1 over u du, luckily, is just like the integral of 1 over x dx. It's just ln absolute value of u plus c. Okay, so just like we did back in chapter 4 when we were doing these problems, we don't want to leave u or the u letter in our final answer, so we're just going to take what u was and plug it back in. In this case, it's 4x minus 1. And again, that absolute value is necessary. And now we've kind of proven that why that common mistake is not true. The integral of 1 over a function is not ln of the absolute value of that function. So don't make that mistake. And if you're always aware of needing to do a u substitution, you'll do fine with those types of problems. Okay, in the first slide, we were just practicing using that new integral, which was 1 over x equals ln absolute value of x. But now let's make sure we're still good with the concept we learned back in chapter 4, and that is this. If we want to find the area between a curve and the x-axis, that's the concept of us needing to integrate. And in this problem, we're trying to find the area from 0 to 3, so it's going to be the integral from 0 to 3 of our function x over x squared plus 1 dx. Okay, so what can we do to solve this problem? Well, you might be tempted, I hope you aren't, but you might be tempted to try to split this into two separate fractions. Unfortunately, we can't do that because we have terms in the bottom, and we can't split a denominator up to simplify. So unfortunately, that's not going to work. What other thing could we do here? Well, there's really not much we can do, unless you realize that if we call the bottom u, that might lead us to a successful u substitution. So let's go ahead and try that. Let's try to call the bottom u and see if that substitution will give us something that we can integrate. So we're going to end up with x over u dx. We have our dilemma where we have u's and x's in our integral, so we need to come over to our u box and take a derivative. The derivative of u is du, the derivative of x squared plus 1 is 2x dx. You'll notice we have an x dx in our problem. I see an x dx right here, which is great. There's no 2 in our problem, and that's not an issue. We can just divide that 2 to the other side, and wherever we see that x dx, we'll replace it with a 1/2 du. And of course, we're just going to send that constant of a 1/2 out to the front. So we end up with the integral of 1 over u du, and now you can see why this problem is in 5.2. We just learned that the integral of 1 over u du is ln absolute value of u, but no plus c because we're finding an area and we have bounds because of that. So we don't need a plus c, we'll just put our little bar notation and then put the bounds from 0 to 3. Because these values of 3 and 0 are in terms of x, we need to plug our u back in, which is x squared plus 1. One other note that I can make here is that the absolute value is not necessary. The reason it's not necessary is x squared will always be a positive value. And if you add 1 to that, that will still stay positive. So if you just want kind of a blanket way to always not mess a problem up, you might want to just always leave your absolute values, and then you'll never have to worry about thinking, should you take them off or should you not? But from time to time when I do these problems, I'll be thinking about that. So if we can take the absolute value off and that's allowable, I will do that. Okay, so let's go ahead and apply the fundamental theorem of calculus. The fundamental theorem of calculus said that we have to take the top bound and plug it in. So 3 squared plus 1 is 10. And then we're going to take the bottom bound and plug it in. 0 squared plus 1 is 1. So we're going to get ln 10 and ln 1. And then the fundamental theorem of calculus says we have to subtract those two values. And then that 1/2, since it's a constant being multiplied, just stays out in front. ln 1, if you remember from 5.1, or if you just remember this from prior math classes, is just 0. So we just end up with 1/2 times ln 10, and here I'm going to write out the decimal as an answer as well, 1.151. Okay, one more example here. Probably looks very complicated, and if you remember something I said in the last slide, you might believe it's an impossible problem. I said in the last slide we can't integrate ln x, or we can, but we are not going to see problems like that unless you get to a Cal 2 class. So you might see this ln x here and go, wait a minute, we might not be able to do this problem. But let's kind of just proceed with some observations here. Maybe it actually will work out. So the first thing I'm going to do is split this into two fractions. Unlike the first example I did, where I circled these two and these two, and I said we can't split it because we have terms in the bottom of this fraction. In this second example, we can split it. We have factors in the bottom of this fraction, which means we're multiplying. So we can split it into two separate fractions. That is allowable. So think back to the idea of a U-substitution. A U-substitution, or at least one of the ways I described how you know a U-substitution can be used, is do you see a function and its derivative inside of your integral? I think for most problems, I probably said, do you see stuff to a power or not a plain x or something like that? But don't forget, there was another way we could identify a U-substitution, and that was, do you see a function and its derivative in an integral? And in this case, we do see that. If I call u ln x, you'll notice that we end up with 1 over x times 1 over u dx. We have our dilemma where we have u's with x's. So if we come over to our u box and take the derivative of u is du, and like you saw back in 5.1, the derivative of ln x is 1 over x, and then we'll put our dx. I see a 1 over x dx right there in the integral, so all of that goes away and just becomes du. And that we can integrate. That's the whole point of integration by substitution. We're taking something we can't integrate and transforming it into something we can integrate. Like you saw in the last slide, the integral of 1 over u du is ln absolute value of u plus c. And of course, like we're hopefully accustomed to, we're going to take that u, plug it back in, and I know that looks weird, but we're taking the natural log of the natural log of x with an absolute value around that still, and then plus c. Okay, in this next problem, we're still trying to approach this integral, maybe with this new rule that we just learned in this lesson. So it looks really complicated and long, and if your first instinct is to maybe try to simplify it, unfortunately, there's nothing we can do to really simplify this. So I guess by virtue of that, we'd have to approach this with some sort of u substitution. But you'll notice, if we call the bottom u, that's not really going to help us. The derivative of x squared plus 1 is 2x, and that does nothing to get rid of the top of this fraction. If you switch that and call the top u, the derivative of x squared plus x plus 1 is 2x plus 1, and that does nothing to get rid of that. So a U-substitution isn't really going to work out. So this is, I guess, I don't want to call it a trick problem, but definitely a problem that requires a different technique, and that is this. If the degree of the numerator, which is the highest power in the top, is greater than or equal to that of the denominator, we're going to need to use long division first before we integrate. You might be thinking, uh-oh, you're going to have to remember how to do long division with synthetic division, or maybe the long division method, but luckily that's not the case. With our TI-89, we can use it to do the long division for us. So if you need the little reminder of how to do this, please refer back to the information sheet you got regarding doing algebra and pre-cal on your TI-89. But just as the quick review, you're going to need to use the prop frac command under F2, and that'll get you the long division. So if you need to practice, go back and try that on your TI-89. But ultimately, you'll see that your original problem can actually be rewritten as that, and I'm going to just put the 1 first instead, so we can rewrite our problem as 1 plus x over x squared plus 1. And we can integrate both of these separately, since there's a plus between them. We can integrate 1 separate from x over x squared plus 1. And the good news is I don't need to go over all the steps of integrating x over x squared plus 1, because you just saw that problem in the last slide. So just as a quick reminder, we called the bottom u, and we ended up with 1/2 integral of 1 over u du. So when we integrate 1 with respect to x, we get x. And then again, you saw that the answer from the last slide was 1 over 2 ln x squared plus 1. And then don't forget the plus c. So really the point of this problem was to just point out this little technique we might need to use if you ever see that the highest power in the top is either equal to or greater than the highest power in the bottom. Okay, next example is a little reminder back from 4.1, and that is solving a basic little differential equation here. As a reminder, when you're asked to solve a differential equation, that's just another way of asking to find a particular solution. So to find a particular solution, we need to do two things. We need to find our general solution, which is the equation where we don't know c, and then we can go ahead and find that value of c to find our particular solution. So again, solving a differential equation is just another way of saying to find a particular solution. Okay, so let's find the particular solution here. If you remember, we need to put our derivative into its differential form, which is just a fancy way of saying move the dx to the other side, and then we can integrate both sides. So the integral of 1, there's an invisible 1 here in front of the dy. The integral of 1 dy is just y. So how are we going to do the integral on the right side? Well, in the bottom of this fraction, and I guess before I mentioned that, we can always pull the 3, the constant of 3, out to the front of the integral. But in the bottom, we don't have a plane x. We can't split this fraction up, can't do anything like that. But in the bottom of this fraction, we don't see a plane x. We see 2 minus x. So to get that out of there, we can call that u. If we call that u, we'll end up with 3, because I'm going to move that out to the front, and then the integral of 1 over u dx. Here we have our dilemma of having u's with x's. We can't have that, so we got to come over to this u box and take the derivative. The derivative of u is du. The derivative of 2 minus x is negative dx, or negative 1 dx. I see a dx here. I see a dx here, which is great, but there is no negative in the problem. So we're going to have to move that negative to the other side and get negative du equals dx. So wherever we see a dx, we can switch that out for a negative du. And since that negative is just really a negative 1, I'm going to move that to the front with the 3. So we end up with y equals negative 3, integral of 1 over u du. And like you've seen in every example we've done, the integral of 1 over u du is the natural log of the absolute value of u plus c. Okay, so that's our general solution. We need to plug our u back in, which makes it the natural log of the absolute value of 2 minus x. And now that's our general solution, so we can use that to find our particular solution. So to do that, we need to plug in the point that we're given to find the value of c. And the way they write the point here is in function notation. But remember, the 1 is our x, the 0 is our y. So we have the point 1, comma, 0. So if we plug in the 1 for x and the 0 for y, we'll end up with this. And you'll notice, inside the natural log, we're going to have 2 minus 1, which is 1. And hopefully you recall this, the ln of 1 is just 0. So all of that goes away. So c is just equal to 0. So we found our general solution, we found the value of c, and now to write our particular solution, or to solve this differential equation, we just need to plug in the value of c, which really doesn't need anything there since it's 0. So our particular solution, or the solution to the differential equation, is y equals negative 3 ln absolute value of 2 minus x. Okay, in this last example, we're going to review a little concept we saw back in chapter 4, and that was average value. We want to find the average value of this function on the interval from 2 to 4. So, as a reminder, this is our average value formula, and really it just involves us taking an integral of our function from a to b, and then on the outside of that integral we have a fraction of 1 over the difference of b and a. So to kind of relate it back to the concept that we were dealing with concerning average value was the height of a rectangle that had the same area as the area under a curve. So I don't have the rectangle drawn here, but the rectangle that has the same area as the area under the curve is right there. And we're just trying to find the height of that rectangle, which is called average value. It's the average value of the function from 2 to 4. Okay, so let's set this integral up. Our b and our a are up here on the interval, so a is 2, b is 4. So if we plug everything in, we'll get that version of the average value formula. So we're going to have to clean this up a little bit before we can attempt to do this problem. This constant of 4 I have here, I'm going to pull out to the front. So 1 over 4 minus 2 is 1/2, and then I'm going to pull that constant of 4 out to the front. And then we'll just be left with x plus 1 over x squared inside of our integral. So how are we going to integrate this function? Well, unlike a couple of the problems we saw previously in this section, we have terms in the top of this fraction, so we can split this into 2 separate fractions. If the terms were in the bottom of the fraction, we couldn't do what we're about to do. But since we have 2 terms in the top of this fraction and 1 in the bottom, we can split this into 2 separate fractions. X over x squared plus 1 over x squared. And if we simplify that first fraction, that just becomes 1 over x. And to make 1 over x squared integral friendly, we can move that x squared to the top, but it's going to have a negative power, so x to the negative 2. The reason I didn't move the x in the bottom of the first fraction to the top is we don't need to. We're not going to use the power rule to integrate 1 over x. We know the integral of 1 over x is ln absolute value of x. To integrate x to the negative 2, we're going to add 1 to the power, which is negative 1, and we're going to divide by negative 1, so that's why we have that negative in front of the x to the negative 1. I said something a second ago regarding the absolute value for the x inside the ln. The reason I didn't put that there, and you're more than welcome to put it, is because the 2 bounds that we're about to plug in of 4 and 2 are positive. So we don't have to worry about those numbers being negative. But if you just wanted to play it safe, you definitely could put the absolute value around that x. Since we're integrating from 2 to 4, we don't need to put a plus c since this is a definite integral. So we're going to put that bar notation and put the lower bound of 2 and the upper bound of 4. Since we're trying to plug this in, since we're trying to plug in 4 and 2, I should say that -1 power isn't something we really want to write. So it's better if we change that back to a simpler looking version. So we're going to write that as 1 over x. We'll send the negative power down to the bottom, which becomes positive, and that makes it 1 over x. So now we can go ahead and take the upper bound and plug it in. So we'll end up with ln 4 minus 1 over 4. We can take the lower bound and plug it in, which is ln 2 minus 1 over 2. And then we'll take those two values and subtract them. And just take note that constant of 2, I'm just leaving in front of everything before we attempt to evaluate this. Because of space and the steps probably getting a little too long for the sake of this example, I'm going to kind of skip over a few steps and just have you kind of try your best to see if you can simplify this expression to be ln of 4 plus 1/2. This is going to require some of your natural log skills and your algebra skills to deal with these fractions, but attempt to see if you can simplify this to just be ln 4 plus 1/2. Assuming you can do that, that's the final answer. And if you wanted to find the decimal of this answer, we would have just, of course, kept the 3 decimal places here. So the technical final answer, if you're going to use decimals, is 1.886.